Imagine you're running a global shipping company. Your customers click a button and you guarantee their package arrives in exactly 2 days. When dealing with millions of boxes, keeping that promise requires perfect coordination. In the software world, we call that ironclad promise to your customer a service level agreement, or SLA. It is the formal contract that says, we will deliver this package in 2 days, guaranteed. To hit that 2-day mark, your internal target is 1.5 days, your service level objective. Tracking real-world delivery times gives your service level indicator. The space between your goal and absolute limit is your error budget. If this buffer fills up, management must step in. You cannot track any of these guarantees, the promises, the targets, or the measurements, if you don't know where your trucks are. Measuring your success requires absolute visibility into every single corner of your delivery network. Traditionally, companies relied on basic monitoring. Think of monitoring like a single red light bulb on a dispatcher's desk. It flashes when a package is late. It tells you something is broken, but it offers no context about why it broke. Observability is different. It is the ability to open up the hood of the system, look closely at the gears, and ask specific questions. It lets you figure out exactly why the breakdown occurred, so you can repair the root cause. To get that deep internal view, you cannot just wait for the red light to flash. You have to place sensors on every single truck, every sorting machine, and every warehouse in your entire network. In software engineering, placing those sensors is called instrumentation. Developers write specific lines of code that act like digital thermometers and GPS trackers. These tiny sensors emit a constant stream of data from inside the application back to the central office. That code is the foundation. By attaching these digital sensors, you take a dark, reactive system and turn it into an environment you can actually measure and understand. Once your sensors are in place, they generate 3 specific types of data. The first pillar is metrics. These are the high-level, historical numbers that provide a broad overview of your fleet's overall health. To collect those numbers, engineers use a tool called Prometheus. It acts like an automated clipboard, continuously gathering raw numerical data, like how hard an engine is working or how much traffic is on the road, from your instrumented systems. Staring at a massive list of raw numbers is not helpful to a human operator. You need a way to translate that flood of information into a readable format. Grafana pulls in raw data and instantly converts it into dynamic charts. These dashboards help spot wide-scale trends, like overall fuel consumption or aggregate delivery speeds. As this line graph shows, you can easily spot a sudden, massive spike breaking the normal pattern. Metrics are perfect for telling you that a massive problem exists. That spike on the graph says something is wrong, but it can't tell you which specific truck caused the traffic jam. That brings us to our second pillar, logs. If metrics are the broad numbers, logs are the detailed, text-based incident reports generated by individual components when something specific happens. Imagine one of your delivery trucks blows a tire. The driver pulls over and writes a specific, detailed note. At 2 p.m., the front left tire blew out on Interstate 95. That note is a log. The issue is scale. A global shipping network generates millions of these isolated notes simultaneously. If they stay scattered in the glove boxes of individual trucks, they are impossible to manage. To manage this, engineers use an EFK stack. One part, FluentBit, acts like a courier that picks up logs from every truck. It sends them to Elasticsearch, a central filing cabinet. Finally, Kibana provides the search bar. By centralizing the data, it functions like a search engine for your system errors. You scan thousands of documents in milliseconds, instantly pulling out the exact report describing the blown tire. Logs answer the question of why a specific failure happened, but reading a report from a stranded driver still doesn't show you the chronological journey of how that package moved through the warehouse hours earlier. To see that full journey, we need the third pillar, traces. A trace is like attaching a highly detailed GPS tracker to one specific individual package. A trace follows the exact path of a single digital request. It watches data move from your website's front door to the database in the back, recording a horizontal timeline for how long each stop takes. When you have hundreds of stages, engineers use a tool called Jaeger to analyze the journey. If one specific step turns an alert color and stretches out longer than the rest, It pinpoints your exact bottleneck. Tying metrics, logs, and traces together used to be quite difficult. Today, the industry relies on a standard called OpenTelemetry. Think of it as a universal barcode system that cleanly links your broad numbers, your incident reports, and your GPS tracking into a single language. By linking the what from the graphs and the why from the reports, tracing maps the exact path for the fix. You finally have a clear view of how the system failed and what needs to change. Implementing all three pillars gives you total visibility. But for a human operator, the sheer volume of that data becomes impossible to read manually. To handle that flood of information, we are now turning to AI observability agents. Think of these as ultra-smart, tireless dispatchers watching every lane simultaneously. By plugging your observability data into modern platforms like Honeycomb or using Elastic combined with Amazon Bedrock, you give these AI agents the information they need to analyze the entire network in real time. These agents use historical data to build a baseline of what normal looks like. By comparing current data to thousands of hours of those historical patterns, they can spot subtle shifts, like a gradual rise in costs or a slight delay in a specific route. This allows them to predict and flag trouble long before it triggers a human-readable alert. With AI in the loop, observability evolves from a reactive dashboard into a proactive defense mechanism that protects the network automatically. Let's step out of the central engineering office and go back to the person who matters most, the end user. When they tap a button on their phone, they expect an immediate result. They don't know about error budgets, the log aggregation, or AI dispatchers. That massive apparatus operates entirely invisibly to them. Modern distributed systems are incredibly complex and inherently chaotic. Deploying deep observability is the only reliable way to tame that chaos. Observability serves as the engine that keeps your promises to the user. It ensures that when your customers click a button, the system delivers exactly what was guaranteed.